We're going to look at a question involving some aspects of the normal distribution. This will not cover everything that we need to know about the normal distribution, but will scratch the surface and help you to revise the concepts involved in this particular distribution. The normal distribution is one of the most important distributions in the whole of statistics. When we define a normal distribution, we need to know the two vital parameters. They are the mean, we term as mu, and the variance, we term as sigma squared. Sigma is the standard deviation of the normal distribution, but the whole distribution is always defined with the mean and the variance in this way. The normal distribution has the following features. It is bell-shaped. It is perfectly symmetrical about the mean, which is mu, and it extends from minus infinity to plus infinity. The total area under the curve is 1. Of course, this is a feature of any probability density function. It's a continuous random variable that we will be dealing with, and the probability density function is somewhat complicated. However, it's not something that we need to be concerned about, because all the probabilities that we will need to use will be either tabulated in tables of the standard normal distribution, or we can obtain probabilities from the ClassWiz scientific calculator. Of course, mu is the mean, and sigma is the standard deviation. Pi and e are two special numbers, but again, we need not concern ourselves with the actual depth of understanding of this distribution. What we need to be able to do is to use the distribution. So let's look more closely at this question. We have a normal distribution. The weight in grams of beans is normally distributed. The mean is given as mu, which in this case is unknown, and that's our first task, to be able to find the value of the mu. If we are working with our ClassWiz calculator, then we will need to work with standardization of the normal variable. That means changing the general normal variable with a mean mu and a standard deviation of 7.8 into a standard normal with a mean of 0 and a standard deviation of 1. Let's first define our distribution. W is normally distributed with a mean mu and a variance of 7.8 squared, 7.8 being in the standard deviation. We know we have a normal distribution, so we know we have symmetry about the mean, which is mu. However, we will need to standardize in this case because mu is unknown. So by subtracting mu, that's the mean, and dividing by the standard deviation, we change our W variable into a Z variable, where Z is a normal variable which is standard 0, 1, mean 0, standard deviation and variance of 1. Having obtained a known distribution, a Z distribution, we can now either go to our tables or we can go to our ClassWiz calculator. In this example, we're going to look at the ClassWiz calculator. We're going to work with the inverse normal. That means we know that the probability of Z being less than this value is 10%, 0.1. And so what we are trying to do is identify what point on the line this value relates to. So into our inverse normal, that's distribution mode 7 on the ClassWiz calculator, the area we are concerned with that's the area to the left, that's 0.1, that's the 10%. Sigma is 1 and mu is 0, and that's because we're working with a standard normal at this point. Inputting this into our calculator, we will get the inverse of this particular value, which will give us the value on the line of minus 1.2815, etc. This is the value of 200 minus mu over 7.8. And so we now have an equation that we can solve by rearranging to give us the mu is just over 209. So let's round that to 210 grams. In part B, we're asked to find a probability now, the percentage of tins that contain more than 225 grams of beans. So the distribution is now identified, with the mean being 210 from the answer in part A. We need not standardise at this point because, of course, the ClassWiz calculator will work with this particular set of information. However, I've chosen to show you the standardisation procedure, and so by subtracting the mean, 210, and dividing by the standard deviation of 7.8, I get the standard variable of 1.92. So either go directly to your ClassWiz calculator. We're now working with the normal CD. We could use the raw data, that's the distribution of 210 7.8 squared, and find the probability W is greater than 225. In which case the value that we're inputting as the lower value will be the value that we're trying to identify, that's 225, that's the raw value. The upper value is somewhere beyond the scale, let's call it 100,000, 1 million, anything large and positive will give us the upper value of the area. Sigma being 7.8 and mu being 210, that will give us our probability straight off. However, if we choose to standardise, then we'll be working with Z, which is a normal 0.1. Same principle occurs. We'll be looking at the lower value this time of 1.92. This is the value we're using here. The upper value, again, something very, very large and positive. Sigma being 1, mu being 0, and again, the values in the calculator, whichever approach that we take, will give us the same value for P. This is the probability that W is greater than 225. The 0.027, that's given us approximately 2.7%. The machine is now adjusted, so we have a new distribution. Let's call it W2 for the variable, which is known to be normally distributed with a mean of 205, as given in the question. And this time the standard deviation sigma is unknown. So again, we need to standardise in this case because the ClassWiz cannot calculate where we do not know the sigma value. So we have a couple of choices here. We know that the 98% of the values are between 200 and 210. And that means that the symmetry of the situation gives us 1% in each tail. So we're dealing with a choice. Either W2 is less than 200, that gives us 0.01, or W2 is less than 210, that's 0.99. I'm going to choose to look at W2 is less than 200, so I'm going to be working with my inverse normal. The area I'm going to choose is going to be 1%, 0.01. The sigma I'm going to choose is going to be 1. Of course, that's the standard normal now, and mu is 0. By using this on the inverse normal, we're going to get a value which relates here to the standardized value of 200, and that's giving us minus 2.3263, etc. Of course, we could have worked with an area of 0.99, and that would have given us the symmetrical equivalent of 210 at this point here. We now know that the standardized value, 200 minus 205 over sigma, is equal to minus 2.326, and we solve the equation to give us sigma.